Hello everyone. Today I will start the topic related to continuous distributions. So let me remind you about this slide that we had in the previous lectures, that what are the differences between these two distributions. Like whenever we are dealing with discrete distributions, each point can contain a specific probability. Like each one of these points, they contain probability, as you can see. If you correspond it to y-axis, which is related to probability, you can find its value. And between them, there are gaps. You see, there are gaps between them. It means that the probability is 0. And look at the continuous distribution. In this case, when you talk about just a point, let's say -1, we are talking about just a line under the curve. So the probability is 0 because we are just talking about one point over infinite number of points. But when you talk about a specific interval like -1 to 0, then it's possible to find the probability. So in discrete distribution, it is possible to define the probability just for a point. But for continuous distribution, we need an interval. Let's say, for example, x between -1 to 1. Otherwise, it will be 0. And for discrete distribution, we know that x less than or equal one number, for example, let's say 2, is not necessarily equal to this one, just less than 2. Right? But for continuous distribution, they are exactly the same because the probability of the point is equal to 0. So, and I already explained why. So there are very important differences between these two, and we should distinguish between them for sure. You already know some famous discrete distributions, and from today, I will introduce you some famous continuous distributions one by one. For some of them, I will explain briefly, but for the important ones that we will practice in our tutorials as well, I will explain in details. So when we talk about continuous distributions, we are dealing with a continuous random variable. So for these variables, we are dealing with real numbers, not just integers. And we should define everything in terms of intervals, okay? Doesn't matter whether this is a closed or open interval, because as we said, point-wise the probability are 0, so we should consider it as intervals. So for continuous version, these two intervals are exactly equal, doesn't matter. We have already talked about this slide before, like we have PDF. For continuous version, we have density function. All of them are kind of probability distribution anyway. So for this one, I cannot define it point-wise like discrete distribution. I should consider it as intervals, which I will show in the next slide. And for the cumulative version, it's very similar to discrete one. The only difference is that we should get in integral instead of summation. So when you want to calculate PDF based on CDF, then you can just get the derivative of that and easily calculate it. It can be easily shown by the theorems also you had in calculus. So please go through your calculus course to remind yourself about integral and series. Integrals specifically, we need them for our continuous variables. And for finding the cumulative versions like CDF from main function as the PDF, then we need to get integral as we explained before, because we are looking for areas under the curve. Now, in case we ask you about specific intervals, like giving you the exact interval A to B, then you can easily calculate it by using this formula. And as you can see here, we have lowercase f, it is related to your PDF, but here we have capital F, which is related to CDF, okay? So in this formula, please pay attention to it so that we should be careful not to mix them up. And in our practices, of course, in our tutorial, we will practice with that. And you can calculate probabilities for intervals easily by getting the integral. And whenever we are dealing with famous distributions, then easily we can find it without even calculating the integral. Remember, for example, for binomial distribution, if we didn't have the table, then we had to have some calculations and we need summation for that. Now we need integral. But if we have the table, usually we try to use table, not even calculate it, because for getting integral, it can be time consuming and sometimes complicated. And for this one, CDF and assign the specific value B. It means that inside your distribution, you specify a number like say 1 and find the cumulative probability, okay? Whatever probability you have under the curve until this point. So for that, when you want to calculate the integral, it's obvious you should start from minus infinity and reach this specific point, because after that, we don't care what's the probability. But what if you consider minus infinity to plus infinity? Then it covers all the area under your curve, everything that you have from minus infinity to plus infinity. So it means that it will cover it all. And what's the probability of your sample space? Obviously, this is equal to 1. That's why you can see here, it is equal to 1. So I already explained about this slide that when we are talking about point probabilities in a continuous distribution, this should be 0. You already know why. And these two probabilities are exactly the same when we talk about continuous distributions. But when I talk about discrete ones like binomial and Poisson, we already know that this is not necessarily the case, okay? So we should be also careful about that. This only holds for continuous distributions. And also for continuous ones, we can define joint densities. Now, here, when you want to calculate PDF based on CDF, then in that case, you should get two derivatives, one for X and the other one for Y. But what if I want to find marginal densities? Then in that case, this function is already given to you. In one of the tutorials, I've already shown you about the discrete one. Now, let's say we have the continuous version. Then in that scenario, this part is given to us. And if I ask you what is marginal density of X, then you can find it by using this formula. So as you can see, it should be based on Y, okay? And that's the thing you should notice carefully. And it makes sense also for the discrete ones. When you wanted to find the marginal ones, then you got the summation based on Y. So Y was equal to 0, 1, 2, 3, for example. Then you could read X's corresponding to them and get the summation. Now we are doing the same, but since this is continuous, then we use integral. And do you remember when this formula holds? It holds when they are independent. So whenever these two continuous random variables are independent, we have this equality. And this is vice versa. I mean, also it holds as a bijection relation. So for continuous distributions, there are also some famous ones like continuous uniform distribution, exponential distribution, gamma, normal, students t distribution. We can also call it t student or t distribution, and chi-square distribution. And for our exams, these three are the most important. I won't ask questions related to these three distributions. But anyway, I'm going through them briefly for these three distributions. I will cover continuous uniform distribution and exponential distribution for today, and gamma, I will talk about it in the next lecture. And normal distribution, we will talk about it in the next lecture. T-student, we will talk about it and we will compare it with normal distribution also later, and then also chi-square distribution in details. Okay, for continuous uniform distribution, this one is very similar to discrete uniform distribution. The only difference is that now we are dealing with continuous random variables. That's the only difference. Now, you can see even for expectation and variance, they are very similar, right? When you want to calculate it and compare it with the previous one, they are pretty similar. And on the picture, now we are dealing with, again, area, you see? Area under this function. So when I want to ask about probabilities, I can ask, for example, what's the probability of A? We are talking about only this area. So it should be an interval for sure. Otherwise, if I ask only for 1 point, you would say this is equal to 0. So it's not a bad idea to compare it with the discrete format again. So for discrete uniform distributions, if you remember, for each point, we have a specific probability. Now, for continuous one, as you can see, we should show it in terms of intervals. Now, this is a straight line, and each one of the points here, if you consider, they are 0, but when we talk about area, then you can calculate it using integral very easily. Okay, and here you can also see that it has two parameters. For standard uniform distributions, it is exactly 0 and 1. But in general format, for the parameters of continuous uniform distribution, you have A and B. These two should be given to you. But if it's only about 0 and 1, we call it the standard uniform distribution. And you will hear a lot about standard normal distribution, and I will tell you why we need such a standard format. Otherwise, we would need to provide you infinite number of tables, which is not possible, and I will talk about it in details when I will introduce you normal distribution. And another famous one is named exponential distribution. This one is actually very useful, and we can use it in several examples. But for our course, I'm going to focus mostly on those three that I mentioned because they are even more important than exponential distribution. But anyway, briefly, I go through it to let you know how it works because it's very easy. Just if you know, for example, Poisson and binomial, this one should sound easy as well. But the thing to notice is that exponential distribution is a continuous distribution. That's a big difference between this one and Poisson distribution, for example. Here again, we can use lambda as the parameter. So the parameter is exactly the same, but now we are dealing with the continuous version of it. But the formula also is different for density function here comparing to the probability distribution, which I've given you for Poisson distribution. Like here, for fx, you should use this formula. Okay, and for expectation and variance, this is different from Poisson version, right? For Poisson, do you remember? Mean and variance were exactly equal to lambda, but here is the inverse, and here it's not just only inverse, it is powered by 2, okay? So there are big differences also between Poisson distribution and exponential distribution. So if I just briefly want to remind you, like if I consider the cumulative version, like CDF, capital F, then for Poisson distribution, you can see that it can increase exponentially. And for exponential distribution, you can see sometimes the same trend. But what's the difference? In Poisson distribution, as I said, this is a discrete one. So everything is pointwise. So it means that each one of these points have a probability, but these lines actually don't exist. There are gaps between them. So the correct format to show it would be just points like this, okay? But sometimes when you see, for example, in some pictures for Poisson distribution that they show the line, it's just to show the trend. Otherwise, we don't have any line between these dots. Also, for the general discrete case, like for example, uniform discrete case, you see just these points are good enough for us. You don't even need to show them like such lines like bar chart, okay? And even if I show it like this, it sounds like a continuous uniform distribution now. So generally it's better to show everything point-wise instead of showing the trend for avoid confusion. But anyway, what I wanted to show you is that they could have exactly the same trend, but for Poisson, for example, we are dealing with points like this. And for exponential one, we are dealing with such a function. So every time you want to find the probability, you are dealing with intervals, not point-wise probabilities, okay? So there is a famous property about exponential distributions named memoryless property. This property is very useful, and usually for such distributions that the past doesn't matter anymore and you want to move on to the next step, then memoryless property can be very helpful. And such distributions, we can also use them in stochastic processes. But I will show you in the lecture of stochastic processes. We can show it by binomial and Poisson distribution instead to consider each part point-wise and not to go through the continuous version. That's why we don't mention about exponential distribution there that much. But anyway, we use it somehow about the memoryless property of it because that can be very useful. So here in this case, for example, let's say if we know earthquake in a specific region follows exponential distribution, and I know that what is lambda, let's say we expect one earthquake each 10 years, then if I know that it exactly follows the exponential distribution, the interesting part is that if I know in the last 9 years we didn't have earthquake, then you expect, for example, in the next year, there's a high chance for earthquake, right? But if I tell you, for example, earthquake follows exponential distribution for this region, then it means that you forget about the last 9 years and still use the same lambda for this one, okay? So it may be confusing for you, but of course, if you are interested in such things, go through the examples in the book. And if you have any questions about them, for sure, we can talk about it. But anyway, I'm not going through them for this course, and I won't give you questions related to that in the exam, because for us, normal distribution, t-student, and chi-square are very important, and I will tell you why also when I will explain those distributions, and we will spend lots of times for them. Okay, guys, that's for today. I will see you guys for the next lecture.